Monday, February 24th. This is CS 746. Today's lecture is going to be on variable selection 1. If I do this right, it's going to be a short lecture. I've got a few topics we want to talk about, but I'm preparing for the midterm and the other class I'm teaching and want to make sure I have the time to put the exam together. Also, my car's battery died, so I've got that to deal with today sometime too. Before we jump into the lecture, let me go ahead and pop up a few notes here. Let's see, we're still waiting to get the linear regression lectures posted on YouTube. They're available, but if you need them before we get them up there, they should be up there pretty soon. On Wednesday and Thursday, I intend to do a lab on data visualization in Python. What I have mostly on that is a demonstration of Microsoft Power BI, Power Business Intelligence. Of course, Microsoft, I pull up the web page and they want to talk to me, of course. But it's a useful tool for doing visualization easily for people who are not data scientists, right? Who are not necessarily technical. Of course, in data science, we can use things like Matplotlib, Seaborn, to do all kinds of visualizations. So we'll discuss those in the lectures on Wednesday and Thursday. Basically, that'll be kind of a lab thing. And then we're going to try to do a lab on the Power BI where I'll ask you to do some visualizations in Power BI in class and submit them. So it's going to be simple discussion on Wednesday and Thursday's classes. Okay, so that's my heads up for what's coming. Lab Wednesday, Thursday. Do try to be here. So for today, we're going to start talking about variable selection. Now, the midterm exam is going to run up until linear regression. And at this point, it is not our intention to put variable selection on the midterm exam. We're going to have that for after the midterm. But we're going to cover the topic now because it's important to understand it so we can get going on our projects, right? So, and we'd already kind of hinted at variable selection in our previous lecture. We're talking about how some variables are better than others. You know, some features are more useful. Some features have collinearity. There's all sorts of things you have to deal with when you're trying to pick out what is the best model to make. And of course, that is variable selection that we're discussing there. So in the course outline, we've done a whole bunch of stuff. We still haven't gone back and done our data visualization lab. Again, that's, you know, going to be Wednesday. So we're down here to variable selection. What is it? Well, it's just basically picking the subset of features that are the most relevant in your data set in order to build your machine learning algorithms, in order to work with your data. There's a great link out here at Kaggle.com where someone has posted a comprehensive guide on feature selection. So don't, you know, rely only on me. There's lots of useful information out there on the internet. And this is a, you know, an interesting thing to make use of if you want to. So that's available as a link. So why do we want to have feature selection? Well, we get a better, more accurate, more representative model. Of course, the model is always, you know, a simplification of reality. It is never going to be as good as a prediction, never perfect predictor, right? Science fiction novels notwithstanding. But we can improve our predictions by making the correct variable selections. Also, it's easier to interpret. The fewer things you have to look at, the easier it is to understand, right? So we've got some of our data sets for the project have just tons of variables, lots of lines in them, right? With data science, of course, that is the whole point of data science, is to be able to work with large chunks of large amounts of data. But for us as humans, it's easier if we can find some way to simplify our models, right? It takes less time to train a model with fewer features in it. It reduces the risk of overfitting. Again, too many features, it'll start memorizing little random fluctuations in there, right? So there's a higher risk of overfitting. It's easier to implement. It's a reduced risk of data errors. You eliminate variable redundancy. If you have two different features that are the same thing, you don't need them both in there. And of course, there's the issue of bad learning behavior and higher dimensional spaces, as we talk about. There's what we call it, cube squared law in biology is the length of an animal doubles, its surface area increases by the square, and its volume increases by the cube, right? So and you get into higher and higher dimensions, your amount of empty space grows and grows. So there's 3 different feature selection techniques. We're going to discuss 2 of them today. We're going to go into the 3rd one in the next lecture. So filter methods is our first one. I'm sorry. Wrapper methods is our second, and embedded methods is a third. What is a filter method? Well, it's a pre-processing step. You've got your data. You don't go out there, you do EDA on the thing, you look at your data, you say, well, this variable is useless. You're going to filter it right up front. You're not even going to consider it in your machine learning model. You're going to say this variable is useless. So you're independent of machine learning algorithms before you even get to the point of doing that, right? You're just looking at the data. You select your scores on statistical tests. You go out there and use all the traditional statistical methodologies, do an ordinary least squares regression, look at the R-squared values, look at the ANOVA variables, things like that. And you're basically going to filter some of the variables out at the front, right? And there's reasons for doing that. So these rely on the characteristics of the data. We're not looking into a model to dig things in there and learn too much about it, right? But we're looking for the correlation with the outcome. We're not using any machine learning algorithms, therefore it tends to be less computationally expensive. It's an easy way to clean things up, save processing time. It's usually not as great as using a wrapper method. The wrapper method is wrapping your features, your model building inside something that's iteratively checking things out, right? So, but this is well suited for quick screening and removal of basically irrelevant features. The basic features are we've got some what we call basic features. We got univariate feature selection. We got information gain. We got looking at the Fisher score. We have the ANOVA F value for feature selection, and we can do correlation matrices, maybe with a heat map to understand what of our data looks like it's useless. Basic methods, straightforward. It's just remove constant and quasi-constant features. So if you have a measurement, if you're trying to do some predictions based on the weather, right? Kansas is all over the place. But if you try to do predictions based on the weather, in like, I don't know, Panama City or something like that, the weather is the same all the time. It's useless, right? So, yeah, sometimes you've got a feature that literally has the same value for everything. Other times you've got a feature that has the same value for almost all observations, most of the observations, right? Little variant. So if you've got a feature that has all the data is constant in your data set, you have no prospect of that feature giving you different values, then that's not going to be any use in predicting your dependent variable, obviously, right? It has to change in order to have any predictive value at all. A quasi-constant, now, usually quasi-constant features where almost all the values are the same are not helpful, but there are cases where there can be an exception where you've got a quasi-constant feature. I mentioned temperature in an equatorial context, right? Well, you can have temperature changes. That's not a perfect constant feature. It's quasi-constant, and it can be very, useful. If a hurricane comes moving in, clouds block out the sun, the temperature drops. Maybe your temperature is predictive of something, in your whatever kind of model you're trying to build, right? So you have to be careful when you're removing quasi-constant features. There's a simple way to do this. You can use the sklearn toolkit. And basically, you set a variance threshold on the sklearn. You go up here, scikit-learn, variance threshold out here. If we just go out to scikit-learn, we can see the documentation is easy to find. And basically, we just set the variance threshold on our feature selection method on our selections. And then we can tell ourselves if a variable is constant, right? By default, sklearn will automatically throw away variables from the model that have no change in the values, right? We can set the value to basically a percentage, a real number between 0 and 1. It'll give a a threshold of things that have below a certain level of variance. Would eliminate those automatically for us, right? Next, past our basic selections, those are easy, right? But you don't usually get that kind of a clean situation in your actual data. Usually you've got to do something else to see if you've got some good filtering to be able to do. So some of the best, so basically univariate features selection methods. We're going to use univariate statistical tests like ANOVA. We said ANOVA in the previous lecture. We said we got a set of variables that we're holding as control variables, and we're asking ourselves whether the new variables are predictive or not, are useful in our model. We're using an ANOVA test for this, so this is kind of a pre-processing step. We use an F-test. We estimate the degree of linear dependency between two random variables. We assume that there is a linear relationship between the feature and the target, and we assume the variables follow Gaussian distribution. So it's not, a normal distribution, right? Gaussian normal. Apparently, Gauss was a very normal person. That's yeah. We got some assumptions we make about the data in order to apply these, in order to apply ANOVA testing, right? So some of the simple ones: select k-best. If we have 20 features and we do a select k-best on our model and say get 3 features, it'll give us 3 features with the highest R-squared values, the lowest correlation with other features, things like that. So it's going to try to use the scores, and we have to decide what scoring metric to use. We have to select a scoring function. We'll get to that on the next slide. Select percentile, whatever our scoring function is, it'll remove all but that percentage. So we can say select percentile set to 10%, and we'll only get the top 10% of the variables. We can do generic univariate select, where we actually have a configurable strategy to use. So we can, give it different, more complicated approaches. So we can use a hyperparameter search, right? Select F, select FDR, select FWE, select RFE. These are all feature selection techniques that you can see in the documentation for scikit-learn. So the scoring out function returns univariate scores, optionally p-values for those scores. Right? So the higher the score, the better. The higher the score, the lower the p-value. And basically is saying how important this variable is, how uncorrelated it is with the others, things like that. So the default is to use F classification using chi-squared algorithm. F classification, of course, each of these is a link directly to the feature selection. And we are in feature selection documentation, but we're down further in there. So each of these discussions here, you can go ahead and get the actual details of it. I'm not going to spend time going through those right now, but it's worth pointing out that we do have these. So we have, again, classification and regression. Those are 2 different things. Classification is basically dumping things into buckets with labels on them. Linear regression is, of course, drawing that fitted line that gives us, infinite extension in both directions, whether it makes sense or not. So we're going to do a linear regression classification, or linear regression scoring functions. Mutual information methods can also be useful in here. These can capture like any kind of statistical dependency. If we use ANOVA, it's a parametric. It is a distribution. We can use non-parametric tests on here, so we can capture things that are not normally distributed, things that we don't have a lot of values for, right? The thing about a non-parametric test is, of course, in order to have an accurate estimation, you have to have more samples to work with, because when you have an assumption about the underlying distribution that's known about that, then you can kind of guess where things are. obviously more accurately than if you don't know what the underlying distribution is, right? Information gain. Mutual information measures how much information the presence or absence of a feature contributes to making the correct prediction on the target. So like if we're doing a regression, we add the feature, how much does our sum squared of error decrease with adding this new feature? How much does it contribute to making a prediction? Right? If we're doing classification, we have labels on things. We're telling it, trying to see if we can make our model match to the labels we already have been told are accurate. And so the error rate, how much does adding this feature decrease the error rate, right? Now we can do this with dependent variable or the independent feature variables as well, not just saying how good does it add to predicting the target variable, but how good do the other features work in predicting this particular feature? Is this feature useful, right? If it's predicted very highly by the other features, then it's not necessarily a useful feature. So mutual information basically measures the information that X and Y share. We get a metric. If these two variables, X and Y, are independent, then knowing the value of X gives you no information about Y. Your correlation on your linear regression line, your slope is going to be 0. It's random scattering of dots. Your mutual information is 0. On the other extreme, if X and Y are deterministic functions, right, then knowing X absolutely determines the value of Y. And your mutual information is the same as the uncertainty contained in Y alone. I'll link here for further reference if you want to read about mutual information of two random variables on your own time. It's worth looking at. So we can use mutual info classification, mutual info regression. Mutual info classification is taking a discrete variable. We've got, basically labels we're assigning it to. And it's a non-negative value which measures the dependency between the two variables. If and only if they're independent, we get a 0. We almost never get 0 in real world, right? Higher values mean higher and higher dependency. This uses non-parametric methods based on entropy information or estimation using k nearest neighbors distances. So we basically have, imagine we're graphing it in space. We've got a prediction that this particular value is in class A and this other value is in class B. We look at the nearest neighbors and how good are we at predicting things based on, how well we distance from the neighbors, right? And we'll get into that more later. It can be used for univariate feature selection. Now, mutual info regression, I think it's amusing here that if we look at this by blinking between here, we don't see a whole lot of distances or differences, right? Again, mutual info regression is for a continuous variable. Same thing, literally, so that's the only difference. If we've got numbers that are, floating point values, and we're trying to see how much mutual information there is between those. It's basically using a regression ability instead of a simple classification. The Fisher score is our next method, and this is the chi-squared implementation in the scikit-learn. And for each non-negative feature in the model, it will give you a chi-squared statistic. And then you can use that statistic to evaluate the categorical variables in a classification test. So you look at the observed distribution of the different classes among the different categories of the feature, and then compare that against the expected distribution of the target classes, regardless of the feature categories. And so the Fisher score kind of gives you an estimate for how good is this variable at predicting the actual classes that we're seeing in the model, right? ANOVA. And of course, this is the most popular way to do it. Analysis of variance. We're taking ANOVA if we're categorical using chi-squared, which we already talked about, Fisher score on here. So we calculate a chi-squared statistic between each feature and the target. If we're quantitative, we compute the ANOVA F value between each feature and the target vector. The F value scores, we group the numerical feature by the target vector, whether the means for each group for the individual features are significantly different. Okay. So finally, correlation. Again, we're still on our filter methods. We're still trying to filter things out up front, not getting into any heavy-duty machine learning. We're just trying to say, you know, we use these techniques to eliminate things from further consideration. And of course, correlation is a variable is highly correlated with the target, obviously, right? But the variables should be uncorrelated with each other. Because if you've got predictor variables that are highly correlated with each other, you've got redundant information, right? Correlation feature basically evaluate subsets on the features on the basis of the hypothesis that good feature subsets contain features that are highly correlated with the target, yet uncorrelated with each other. And we'll get into looking at this, but basically you look at do your correlation matrix, you do your heat map, you see things that are, you know, correlation between the two variables of 0.96 or minus 0.96. You say those variables are highly correlated with each other. Maybe I don't need both of them in my model, right? So basically that's what we're looking for, feature correlation values that are lower, close to zero, whether it's negative or positive. But we want to see correlation with the target variable that's high, right? So in reality, you're never going to see two features that are completely uncorrelated with each other. That's just not the way the real world works. So we're looking for not zero correlation, we're looking for low correlation, close to zero, not at zero. All right, so that was basically the filter. Again, what we're doing is we're starting with our data. We're doing exploratory data analysis on it. We're looking at analysis of variance. We're looking at correlation. We're looking for different things, and we're saying, well, you know, this variable has only one value for every observation. It's not useful. This variable has a correlation with another variable of 0.92 or something like that. It's not particularly useful. Maybe we'll get rid of it, so on and so forth. Once we get past that, we're going to start looking at wrapper methods. Okay? And, you know, you don't have to do filtering. You could just turn your computer loose on it. I mean, this is the cool thing about the Moore's law, that computers get, you know, more powerful every year and a half. They double in power. It's just a rule of thumb, but it still is holding true. Computers keep getting more powerful all the time. You could, in fact, be lazy and just turn it loose on wrapper methods, you know, and not do filtering at all. You know, just make your CPU on your computer do the work for you, right? Or the GPU in your NVIDIA card that you bought. Yeah. So in wrapper methods now, what we try to do is we use a subset of features, we train a model, and then we decide whether to add or remove features from the subset. We're basically doing a search problem. Again, these are computationally expensive. What we're doing is we're not saying these features look useless. We're throwing them away, never looking at them again. We're saying we're going to take all the features. We're going to see if this combination of features is better than this combination, is better than this combination, and so on and so forth. So if we do it you know, exhaustively, we can have just tons and tons of different runs of the model with different features. The 5 basic wrapper methods are forward selection, backward elimination, exhaustive feature selection, recursive feature elimination, and recursive feature elimination with cross-validation. Forward selection starts with an empty model. No variables at all, right? And start adding variables based on how significant they are by using whatever scoring function we choose until we reach a pre-specified stopping rule, or we've got all the variables included in the model. We've run out of variables. The most significant variable can be chosen by several different metrics. We can choose the one with the smallest p-value, the one that is, you know, least likely to be uncorrelated with the target. The one that provides the highest increase in R squared, and these are all correlated very strongly with each other, these three different metrics, or it provides the highest drop in modular residual sum of squares compared to the other predictors under consideration. So we have to choose a stopping rule. So for instance, we'll say if our p-value for our variables exceeds a threshold of 0.15 or something like that, we're going to ignore those variables. If we set a p-value of 0.5, we stop there. We can set an R squared threshold, an RSS threshold. When we reach this state, forward selection terminates, returns a model that only contains the variables with p-values bigger than the threshold, R squared, or p-values less than the threshold, R squared higher than the threshold. Residual sum of squares change, above a certain threshold, things like that. So what is a threshold? We can go ahead and set a fixed value. I want to do a model that's 95% confident. So I'll just set my confidence interval to my p-value to 0.05, and I'll just run my model until it pulls in all the variables that have a p-value less than 0.05. Or maybe we could do 0.2, right? Depending on how many features we feel are important. Or we can use information criterion. There are two different information criterion that are popular, the Akaike and the Bayesian information criterion. So if we choose a fixed value, the threshold is the same for everything. The Akaike and AIC and BIC basically move the goalpost. So with every new feature that you add, it needs to be a little bit, the threshold for the p-value drops a little bit. So you might start off with a p-value of 0.05. And then for the next one, you say your p-value needs to be 0.048, 0.046, and so on. And this is all calculated automatically, right? So basically, you're just saying in order to add more features, it needs to be more and more useful. The point being, we don't want to have too many features in our model because this, as we said, increases the risk of overfitting, increases computational complexity, makes it harder to understand the model, just makes things take longer in general, right? So AIC and BIC, these are the formulas for them. N times the natural log of the sum squared errors minus n times the natural log of the number of observations plus 2 times the number of features plus 1, okay? Over here, we're actually saying adding another penalization term where the Bayes information criterion is the number of features times the natural log of the number of observations. We actually, if we go in and compare these, what we see is that Bayes information criteria, because of this extra term here, basically penalizes the free parameters more strongly. So if you run the same model wrapper method using AIC versus BIC, generally AIC will end up with more features in the model than BIC will. Okay, and this is all goes back to the entertaining story of the the Bayesian statistics wars among statisticians in the United States and England back in as late as the 1990s. They were still arguing whether Bayesian statistics were legitimate or not. And it's really there's a great book out there, The Theory That Would Not Die, if you're into reading that kind of thing. And you're like, this is boring. But anyhow, it's really fascinating to see how you'd think statisticians would be like, we're just looking at the numbers. We're going to use the data. We don't have to have any arguments that make sense, but they were arguing about whether, they needed this criterion. Was it more useful than this one? Yeah. So these days, BIC is tends to be preferred. There was a period of time where AIC was the only one that was available, right? Kaike generally tries to find the unknown model has high dimensional reality. The models are not true models. It's not consistent, could overfit. And again, it's derived from 1930s era frequentist probability models. Of course, Bayesian models existed even in those days, but academic statisticians thought they were just, too ad hoc, not mathematical enough. They've changed their mind. The usefulness was the convincing factor in there. Bayesian information criteria comes across only true models. It's consistent, unlike the Akaike. It suffers from the problem of it could eliminate too many features and underfit. And of course, obviously from the name, it's derived from Bayesian probability. Backward elimination. This is the opposite of forward selection. You start with a model that has no variables in it and add the features. Well, how about if we start with a model with every feature included and then find the most useless feature and throw it away until we reach a threshold? Same kind of thing. Begin with a model, it's called the full model. Start removing the least significant variables until we either reach a pre-specified stopping rule or there's nothing left in our model. So determining the least significant variable, again, we're using a scoring function here. We look for the highest p-value, the lowest drop in r squared, or the lowest increase in residual sum of squares. So, basically we're asking ourselves, which one is the least likely to be statistically significant, highest p-value, or which one, if we look at how good our model is for the full model versus the reduced one, which one gives us the least decrease in accuracy of our model. So forward stepwise versus backward stepwise. Backward stepwise has the advantage of considering all variables simultaneously. It will end up with a larger number of variables probably than forward stepwise. Forward stepwise is something you use when you have a very large number of variables. For instance, if your sample size is not even as big as the number of features you've measured. If you have way too many features to look at, then you might consider using forward selection because you're basically computational. Complexity of using the full model with lots and lots of features is significantly higher than considering fewer features, right? So the forward stepwise would favor a smaller model with fewer variables. Rule of thumb, unless the number of candidate variables is bigger than your sample size or your number of events or whatever you want to call it, recommendation is to use backward stepwise. Or, best of both worlds, you can do forward and backward selection, where you alternate adding and removing variables until you reach your best model. If you have collinearity of your variables, backward stepwise selection has an issue where it may be forced to keep things in the model because they all got kind of a similar p-value to be throwing away, right? So whereas forward stepwise would pick one, add it. It would be very sensitive to changes in your data, but it would pick one, add it, and then refuse to add the other multicollinear variable to it. So there are issues with backward stepwise selection, which we deal with by looking at the collinearity itself up front using our filter methods. Right? Understand where your collinearity is in your model. Stepwise selection is a reproducible and objective way to reduce the number of predictors. In other words, if you have the same data, you're in the same forward stepwise or the same backward stepwise, you're going to get the same results every time. Right? We would like to think that expert opinion is a great way to do it as well. I think these are the important features because I'm an expert. I've studied this for 40 years and I know everything, right? But we have to admit that expert is often biased towards one's own beliefs or hypotheses. But automated variable selection cannot and does not replace expert opinion. So if someone, basically the rule of thumb is if your expert says this feature is important, and your model says, it's not that important, keep it in. If your model says, maybe this feature is important, but your expert says, I think that's useless. Well, you might still keep it in. Your expert's opinion is more important when they're saying this is an important feature than when they're saying it's a non-important one. There's a, I won't go into that. There's a reference to Clark's third law, but you can look it up yourself. Anyhow, but so, again, your experts generally know more about the data than your machine learning tools can figure out. They've got memory, things like that. If something's important, they'll tell you. If something's not important, they could be wrong. They could be wrong about it being important too, but they're more likely to cause problems if you ignore their advice when they say something's important, right? So where automated variable selection is most helpful is in doing EDA. If you're working especially on a problem where there are no experts, right? So if there are no experts, you're working with something new. There's not a lot of background knowledge, new research topic. Found a great thing for your PhD thesis. You're riding high because you got something brand new that no one else is dealing with. In that case, maybe let the automated variable selection give you some suggestions. Pay attention to those. Take them with a grain of salt. You're becoming the expert now, but understand what it's telling you. Advantage of stepwise selection, it's easy. You just say, I want to set my threshold, go. Right? It improves the generalizability of your model. It yields a simple model. It's objective. It's reproducible. Limitations. It doesn't consider all possible combinations of potential predictors. Suppose we have two features that are collinear with each other, but one of them is better at predicting the target variable than the other. It may not be a huge difference, right? But we have to consider a model with one versus the other, see which one is better. If we're doing forward stepwise, we're just adding one feature at a time. We're going to pick one. We're going to throw it in. We're not going to even look at what the model would look like if we had selected the other one. Right? That's the algorithm for forward selection. Similarly for backward selection, we're going to pick the one that looks worst. We're going to throw it away. So we have to have another consideration. The next topic is going to be how do we do, we can use exhaustive, right? Every single combination of features, right? That gets computationally expensive, but that would cause us to find the best one, and we'd know we'd found the best one, right? So stepwise selection gets an unstable selection of variables. In other words, if you have a set of data, you run it through, you'll get a set of features that are selected. If you get another set of data collected, maybe some different sensors, or you get data from Wichita and then you get data from Topeka or something like that, right? And you try the different data, you might get different features that are said to be more important. It doesn't consider causal relationships between variables. Sometimes you collect features where one feature is actually causing the other one. They're literally related, right? As we talked about, height and weight are strongly correlated with each other, right? Of a person. So here's our limitations. We get biased regression coefficients. So if we do stepwise regression, our regression coefficients will appear larger than maybe they are. Our confidence intervals will look narrower than maybe they are. We'll feel that we're more confident about our data. Our p-values will appear smaller. Also, they can be invalid as we start pulling these things into our value feature, into our model, because we're looking at the p-values individually, separate. Our r-squared will appear larger than it might actually be in reality. So let's talk about exhaustive feature selection. Again, we go out there and we pick the best subset of features. We consider with no features, we consider one, we consider two, all combinations of two, all combinations of three, all combinations of four, right? If we have 4 features, we'd be looking at 15 different combinations. So 4 combinations of one feature, right? And then 7, I think. Anyhow, 4 combinations of 3 features, and then all 4 features at once. Did that add up right? 4, 8. 6 and then 1. Yeah, okay. And then we select the one that results in the best performance, as in, say, classification accuracy or F-score or sensitivity or recall, whatever we choose is our performance metric. We'll find the one that's best. This is a greedy algorithm. It considers everything. It's computationally expensive. If you have too many features, it becomes still unfeasible unless you have unlimited processing time and a giant supercomputer, right? And an unlimited budget. So recursive feature elimination performs a greedy search to find the best performing feature subset. So we start a feature. Instead of just finding the feature with the highest p-value and throwing it away, we're going to throw away every one of the features one at a time. So consider the full 4. Again, here we had 4 features. We consider all 4 features together. Then we consider these 3, these 3, these 3, these 3, all the combinations of 3 features. We find the best performing one of those, throw away that variable, keep the 3 features that we say are best, and then so on and so forth. We continue, again, exhaustively looking at all of our possible values, and then throwing away the worst one at a time. You might say, well, this is probably going to be the one with the highest p-value or the one with the, lowest decrease in R-squared, and that's probably true. But you don't know that unless you run an exhaustive feature selection, right? In the worst case, if a data set contains n combination number of features, we'll do a greedy search for 2 times n combinations, right? For today's lecture, recursive feature elimination with cross-validation. And now we're out there and we're saying, instead of removing 1 feature at a time, right, we're going to remove 2 features at a time using recursively feature elimination. So we'll come back there and then compare the models using the accuracy or cross-validation score, the ROC-OC, receiver operating characteristic area under the curve. This is also called the F1 score, where we're looking for the model that is best at predicting the target variables and has the least amount of correlation between the features. And this is going to be computationally expensive, but it's less so than exhaustive methods. Right. Okay, for further exploration, you're down to the last slide here. You can go out to sklearn feature selection. As they point out, you just go out there and Google features feature selection sklearn, and it'll take you straight to the page. And you need to understand these. I'm not going to go digging into these in detail in here, but if you're going to do data science, you need to understand what's going on in all these different approaches. So you'll have to look at that at some point, whether you manage to get through this class without paying attention to that or not. You'll have to look at it eventually. So you might as well do it. MLextend is an alternate library that some people find preferable. And then Polars. Last year, Polars, I found out about this. Pandas, they say, is cute, but Polars is better able to hand it. Polars is in fact a competitor for Pandas. So data frames for the new era, blah blah blah, get started, right? So this is a open source. The developers of Polars saw that there were certain things that they didn't like about Pandas that were a little bit clunky in some of the operations, things like that. Pandas is slowly cleaning up things. It's actually an improvement of a previous model, NumPy, which did simple number calculations, right? So the cool thing about open source is that if you don't like something, you can just create a new package and go out there and release it. The drawback of open source is that if you're using open source software, you always have to be aware of the possibility that something different can come along. So we're saying we're going to use sklearn and pandas as the default in this class. I brought up the slide for pullers right before class started, and a student over here is like, "Oh, I saw that just the other day." And yesterday? Yesterday. He's all, it's interesting. It's exciting. If you want to try to do your project in pullers and ML extend, let us know. If it goes wrong, you'll have to come back and fix it, right? So, and those could be better tools. And I'm not, I don't have all the time in the world. I can't sit down and spend all my time evaluating all the different open source packages that come online all the time, because there are always new things coming up there. But if you're interested in it, give it a shot. Yeah. All right, that is the end of the lecture for today. So we have 2 people online. I'm going to go ahead and do the attendance quiz real quick. So I'm going to stop sharing the screen for those of you that are online. If you want to get partial credit for attendance, you can go ahead and type your name into the chat right now. So online. Possible. My assumption is that everybody's going to attend this class in person enough times that no one will need to worry about getting partial credit for online attendance. But just in case, put your name in there, and then if you come back and say, I attended online and I had this thing going on today, I couldn't make it in class, then cool. Stop sharing. Stop recording.